Morning, everyone. Thanks, Christoph, for the invitation. Talk about the global navigation satellite system reflectory, stands here as GNSS-R. Physicist in the geophysics laboratory at the University of Luxembourg. So in this talk, I'm going to give an introduction, what we do, different GNSS signals. Then I will talk about the geodetic GNSS-R, where I talk about the forward and inverse modeling of the GNSS-R. Then I will shortly talk about the extended model, and then I will show some application that we can extract snow depth, sea level. Then I switch to the spaceborne GNSS-R, where I will show how we retrieve soil moisture and ultimate product, and then I the conclusion. So as you know, there are different methods to extract the geophysical parameters such as soil moisture, sea level, and they are very essential for our daily life. We have in situ sensor that we can extract the soil moisture, so they are direct measurement. See here, so we have the in situ moisture sensor, as you can see here, or we have the snow pillow that we can have the snow depths, but we have different satellite mission, as you can see here. So we have this map is a 1 billion NASA mission that can provide the global soil moisture. Then we have GPS, American global navigation satellite system. We have the European Galileo, Chinese Beidou, Russian GLONASS, and then we have some local systems such as QZSS Japan. So some of these systems are active and some of them are passive. Here I'm going to talk about the passive system where we are receiving the signal from the GNSS satellite. So we are not producing the signal. So we would have the receiver just to receive the signal, and then we extract the geophysical parameters. So traditionally in geodesy, we were trying to use to have the time series analysis to extract the plate tectonic. So here you can see a clean time series with no gaps from 2012 to 2023. So by processing this data, we could have different measures. For example, in the beginning, we were using the least square adjustment to estimate the slope of the time series. Then later, we started to use the tailsen estimator, and recently we are using MIDAS to extract the trends of the GPS time series. So as you can see, when we don't have the gaps and offset, it's very easy, and we can extract the velocity, and then we can express that in terms of the plate tectonic movement. But when we have offsets, then as you can see, the data is going to be very different. So there are different criteria and estimator to extract that. And as you can see, one of the most effective one is the MIDAS, median interannual difference adjusted for skewness, that we estimate the velocity or slope of the time series. And as you can see in this simulated signal is very close to the truth data. But when we have these offset and gaps due to non-geophysical phenomena such as instrumental change, or when we have the earthquakes, so we need to somehow take care of this offset. For example, when we want to use this kind of time series to extract the continental water storage from this kind of time series, because as you can see, we have a very clean annual and semi-annual cycle when we don't have those gaps in the red one. So if we can remove those offset, we can extract those kind of geophysical parameters. So the model we use is the least square various component estimator. As you can see, the functional model is here. So we included a second term to automatically detect the offset. So we have the design matrix capital A, where we have a linear trend and annual and semi-annual signals that we extract from MIDAS, and then we have, then we have another term that we include to detect the offset. It's very crucial because if we don't remove this offset, the estimated amplitude of the variation for the signal is going to be very different. So this is the traditional time series analysis that we do in geodesy. But now today I want to mainly talk about another application of the geodesy where we use the noise as a signal of interest, because in those applications we just use the direct signal, as you can see here, the blue one. So we receive the direct signal from the orbiting satellite by our antenna receiver, and we process the data, and we have those kind of time series. But we have the reflections around the antenna that bouncing back to the antenna. So this is a source of noise that we are trying to minimize and remove it when we do the time series analysis. But these information can provide us some useful information to extract geophysical parameters. For example, as you can see here in this simulation, we can have the constructive and destructive phases. So when they are going in and out of phase, we are going to have these fringes, as you can see in the SNR observation over elevation angle. As you can see, the satellites are orbiting, so we have the satellites are rising from 0 to 90, and then they are setting to the horizon. So if we receive this kind of signals, we can have different observation from different azimuth angle and satellite elevations, and then we can extract geophysical parameters. The model in GNSS-R we use is a combination of a trend and fringes. As you can see, it's a function of direct and interferometric power and noise powers, where it's a function of the directional dependent of the gain patterns of the antenna. As you can see, it's a choke ring antenna that we traditionally use for positioning application. Then we have the phase in different direction that coming from orbiting satellite, and then we have the Woodward function here, and then S here stands for the standard deviation of the surface roughness. So if we can extract those phase observation, we can convert them into the different geophysical parameters. So this is the model we use, but as we are dealing with the real data, the data is really noisy, and as I mentioned, this data is not built for this kind of application. So we are trying to make use of some kind of noise which is has been tried last 30 years to find models and improve mathematical models to reduce that. But we are trying to use it to extract geophysical parameters. That's why we call it signals of opportunity. So we develop a model here by including some terms. So what we do, we have a forward model where we simulate the surrounding around each GPS antenna using a least square spectral analysis, and then we use those values as a priori value into the least square weighted least square adjustment to find the corrections using the variance covariance of different satellite tracks from different direction to improve our result. So this is just one example to show that we have different signals. As you can see here, I simulated here signals from L1, L2, L5. As you know, we have 5 frequency on GPS and 2 on GLONASS, R1 and R2, and different antennas. And as you can see, when we change the surface properties from wet soil to the dry soil, the fringe visibility of this received signal is going to change. So if we can extract this observation over elevation angle, as you can see, is changing because the satellites are orbiting, we can extract those kind of information. So this is the real observation we have for one GPS antenna in French Alps. So this is one snowy day, and this is a summer day, and these are the GPS observations. So as you can see, the satellites are orbiting. We have a hole in north direction. It's just because of the inclination of the constellation. The top panel here is for the GPS. The bottom panel is for GLONASS. So as you can see, we have different kind of precision around the GPS. So when we receive this kind of signals. In addition, as you can see, the observations also have different noise level. So when we want to extract these parameters and we want to combine them, we should come with a model to help us to improve these solutions. Again, as you can see, different azimuth angles. The center is the location of the antenna, and when we move around different direction, the properties of the signal is changing depending on the azimuth angle and the elevation angle of the satellite. So we need to come with a solution to improve this solution. One, we came up with the clustering of this GPS observation. As you can see here, I have a cluster of GPS and GLONASS. Different colors are from different GPS satellites or GLONASS satellites. As you can see, I have a very clear pattern for the GPS, as each GPS satellite appears every day at the same location. But that happens from GLONASS every 8 days. So when we cluster them based on the azimuth angle and pseudo-random number, which is the satellite number, we will see that we have a cluster based on setting and rising arcs. But when we do that for GLONASS, we have a lot of cluster with less information. So we, again, recluster them based on the azimuth angle so we can combine all those solutions. So to combine those solutions, we estimate the variance factors for each signal and each cluster. So this is the model we use. We have K for the cluster, J for the each signal, and I is for the epoch. So we are running a moving average over each cluster, and then we use a studentized residuals to estimate the variance factors for each signal. Then we redo that for each cluster, and finally we combine that. By doing that, as you can see, the number of observation increases, and here I show the result when I combine only GPS green, the blue only GLONASS, and then when we combine all of them. So the RMS improved by about 50%. So when we do that. So this is when we combine all the solution, is this one typical station without and with snow. So the red one shows our estimates, and the green shows the truth that we compared, and we have a RMS, great RMS. The advantage of this technique is that you can see that in different time and different direction, we would have different behavior of GPS signal. So this could be used, for example, to see how the snow is melting. That would be very interesting, and now we are working on that. So it also can be applied for sea level. This is very interesting because for sea level, we usually have the tide gauges, but tide gauges are moving with the crust, so they have to be corrected for the relative movement of the Earth. So if we can find a solution to just use one technique to have the sea level in one terrestrial reference frame, that would be very useful, and that would be the GPS signal, because these GPS antennas are installed to link the tide gauge here to the crustal deformation. So the sea level can be isolated from the crustal deformation. But here we propose to use this technique to estimate sea level. It has some advantages, and these advantages, as you can see, the advantage is that there are thousands of GPS stations that the data is freely available, and we can have access to this data to process. This is the distribution of these sites, but it has some disadvantages where we have the vertical velocity, where the sea level is changing. Then we have troposphere, ionosphere, surface curvature of the Earth that is going to impact of the signal, and also the low rate of the received signals. So here we developed a method to include the velocity and acceleration correction, and this is one GPS station in In Australia, as you can see, we estimated the sea level. The sea level is changing about 2 meters. So when we don't correct for the time variation of the sea level or taking into account the dynamic state of the satellite and the reflecting surface, we would have a bias in our system. But when we correct for that, somehow this model take care of the atmospheric refraction, and then we would have a better RMS error. As I mentioned, we have different signals. This is another station in Africa. We tried it for different signals to see if there is a consistency, because as I mentioned, they have different precision, they have different type of signal design, and we see that there is a consistency between all those signals. So we came to this conclusion that there is no systematic differences between those signals, so we can do a combination of these signals to provide this kind of sea level retrieval. So this is one station in Antarctica. It's very critical because it's very hard to maintain the tide gauges there because ice is building up and the tide gauges are going to be damaged. So we have these stations, and this is the footprint around each GPS antenna here. As you can see, different colors are for different GPS satellites. They are rising from 5 to 30. So the variation because of the curvature of the Earth is changing. So we process the data, and as you can see in the Van der Kasteel diagram, we don't have any systematic bias between the in situ and tide gauge, between tide gauge and GNSS observation. And then we estimated the tide, and as we can see that all the main components are retrieved using this technique. This is another station that we installed in Caribbean Sea in Haiti. So it's installed on top of the tide gauge. We wanted to see if the surface roughness of the sea is going to impact. So it should be installed vertically on top of the tide gauge. As you can see, this is the tide gauge and this is the GPS antenna. And again, in the diagram, we don't see any systematic bias, and our conclusion was that this technique can be a complementary system for the traditional tide gauge estimation. This is another extreme case where we installed a tide gauge in Vianden in Luxembourg, north of Luxembourg. They use these pools to generate electricity, so the water is changing by 17 meters a day because they are pumping up water when they don't need electricity, and when the demand for the electricity is high, they open the turbines, and then there are several turbines and they produce electricity. So by applying these techniques, correcting for the Earth curvature at different elevation angle, we could estimate the sea or the pool level by an RMS better than 7 centimeters. We apply this technique for different locations. This is ice in Great Lakes. As you can see, it's a long time series analysis. We could estimate the sea level and isolate the ice from the sea level on this kind of time series. We also could apply that to estimate soil moisture. This is one station in Ludelange where we installed. Here is the location of the antenna, and the red arrow shows the in situ location, and estimate the soil moisture, and we compare that with the truth. And as you can see, we have a correlation better than 88. So this was the ground-based, and then we switched to the spaceborne because if I want to give a story about this spaceborne, the spaceborne GNSS-R was proposed in 1993 by ESA, but it was not well received in the community until there was a classified airplane in the US flying over ocean, and when they were tracking the GPS signals, the location of the airplane was about 100 meters below the sea level. So they could not figure it out, so they contacted ESA if they have any clue what's going on there, and they found out that instead of the direct signal, they were receiving the reflection. So the signal would be biased, and then they would have the negative value. So the observation, as you can see, is again a function of the wavelength lambda, but then we have the gain patterns which are different at different direction and azimuth angle, and we need to model them using different algorithm, and then we can convert this kind of observation to the surface reflectivity. This is just one kind of observation that it provides in South America, and as you can see, all the river branches of Amazon is very clear by just collecting this kind of information. So this is a global map that Cygnus, the NASA mission, provides us. So we have a reflectivity over globe. So we can see a clear change over Amazon or winter and summer period. And then by creating the false color maps, we could see that a lot of properties can be extracted, such as surface roughness, vegetation content, or soil moisture. But this observation has to be gridded. So there are different gridding methods. One is 1 kilometer, 9 kilometer. We can go up to 36 kilometers. So when we gridded using different grid cells, as you can see, the slope is changing. So based on the number of observations. So it's very important to reach a level that the slope is not changing that much and is stable. So we need to have a minimum number of observations. So this is for 2 different locations for 9 kilometers. And as you can see, we need to have at least 20 observations to have a good slope when we want to estimate the soil moisture. This work is part of the work that we are involved with several universities, and we are trying to provide and combine all the solutions. So this is our solution that is provided to JPL, and they are feeding the algorithm to provide a combined solution based on the result we provided. This is a coverage likelihood map of our solution with respect to SMAP, and this is the correlation of our result. So we have a pretty good correlation compared to other sensors that they are not here and are still investigating this technique. So here is just to show this is the unbiased RMS of our result globally, and it's pretty good. And then here we show that the color map of our estimate with respect to the reference, and there is no bias. And as you can see, the cumulative distribution of our unbiased RMS is better than 0.5. This is what is needed for validation and calibration of the space mission. So then we classified our land to different categories, and then as you can see, based on number of observation grades, the result is going to change. So that's a ongoing study that we are working on the number of observation to see how these statistics are changing when we apply that. Then this is another application that can be used for inundation extent map. So we create this kind of inundation maps around the world using this kind of observation based on track-wise observation at different locations when they are corrected for the curvature to see how the world is inundated. Then we use JJR, where we use the phase observation. We don't use signal power, so we have direct and phase ambiguity, and then we can estimate the altimetric result. Here is just one track. As you can see, we reach a good precision, and the average RMS is better than 16 centimeters. So when we want to do that, the main step is to find a coherence of the signal. So different statistics are applied. One is the standard error of the phase noise, and the other one that we are currently applying is the circular statistics. So we are using kappa and zeta, and then when we have a constant term because of the phase, we consider that as coherence. Then we define the semi-coherence and incoherence, and then by doing that, we provide a classification of the ice, as you can see by this map, and then we can provide also sea ice altimetry around the world. Another step that is very important we do is the precise orbit determination, because when we want to do that, we need to find the orbit of the GPS satellites and our flying platform. So we develop an algorithm here where we process several we run it in 5 different steps to improve, to correct for troposphere, ionosphere, and find the location of the GPS satellite, the CubeSats, and then we find the specular reflection point on the Earth. Then we can correlate our estimates to the estimated point. So by that, I leave it here by the conclusion, and I take your question.